So what I'm going to do though today is talk about some of the things that we are doing at the University of Liverpool related to the use of in-painting to control the dose that we put into the electron microscope. And the idea behind this is that if we get better dose control, then we can have better precise images, we can get better understanding of in-situ experiments, and be completely free as much as we can do from the interaction of the electron beam. So let me start by just sort of going through the sort of basic electron microscopy workflow that we're all really familiar with, but it helps to understand where it is that we're trying to get in-painting to come into the system. So if we go through what we usually do in electron microscopy, we do some kind of specimen preparation. Now that could be a very simple specimen preparation. It could just be grinding something up or spreading something on a grid or getting it into the microscope. It could be something very complicated like fibbing out a lamella and then getting that into an in-situ stage where we could do liquid or gas work on it. So there's a lot of things that we could do in the specimen preparation. But we get into the microscope, we then have to align the microscope. When we get the alignment of the microscope as good as we think we can get it, we then acquire some images or some spectra or diffraction patterns or whatever it is that we're trying to do with our experiment. After we get off the microscope, we then try and pull all of those things together to increase the precision of our experiment. We might use some simulations to help us to understand what our experimental conditions are, so it increases our precision. And then at the end of it, we'll run some analytics on what we got. And that analytics might be looking at the image and saying, oh, there are some dislocations there and these are the dislocations, or it might be a distribution of sizes, it might be a temporal resolution, it might be a change that comes out of it. But effectively, that's what we're trying to get out of the final experiment, is the actual quantified result telling us what is going on. Now, if we look at what a lot of the machine or deep learning approaches are doing electron microscopy, many of them are approaching this at the end of the process, which is to say that once we've got all of our images and we're looking at them, we can use machine or deep learning approaches to help us to increase the precision and to perform analytics of what we're looking for. And this could be identification of interesting contrast. It could be identification of structural features, but we're trying to do that at the end of the process. Now, all that is very helpful in terms of the analytics side of things and the final stage of what you want to get out of a microscope. But there are all of the other stages that have gone before it, which are really the same stages that have been there for 70 years since electron microscopy really got going. And so the question we might want to do is to say, well, can we actually go back to the beginning of this and look at the entire workflow from the first stage and say, can we do something with that to allow us to improve everything in the steps as we go forward? And the reason for trying to do this is to increase the speed of the result that comes out. There's a lot of things that speed can help you with. They can help you with avoiding beam damage. It can help you with getting through multiple samples. It can help you do dynamic experiments and see transients that are taking place. So there's a real benefit to all of electron microscopy if we can actually increase the speed. So what I'm going to talk about really in terms of how we're going to incorporate in-painting is really from everything from the specimen preparation, where we're looking at maybe to improve the efficiency of our fib preparation to get better samples with less damage. Looking at the automated alignment of various functions on the microscope so that we can get better acquisition much quicker with lower doses. Then we can integrate our theory with our experiment so that the precision we get out is not a matching of theory and experiment together, looking for the best match. It's more about solving the two together. And then if we get all that, then the final step is we'll get real-time analytics that come out in the end. And so all of this approach is what we've been sort of working on. And I'll talk about various bits of it as we go through this presentation. But our initial goal is that we think by going through this, we should be able to get well into video rate for doing STEM experiments, everything up to four-dimensional STEM if we wanted to do that at video rate. Okay, so in terms of going through this, I wanted to start with this. There are the things that people are used to talking about in terms of deep learning approaches, artificial intelligence, whatever you want to call it. It's really the big data challenge, which is to look at the kinds of big data that's out there, or in terms of a scientific approach, the kinds of things that the materials genome can generate, or high throughput synthesis and diagnostics can generate. And we have a group at Liverpool that's doing a lot of this at our Materials Innovation Factory, where they're using robotics to do a lot of experiments to generate big data to get us to the point of identifying trends in that data that can help develop new materials for different applications. But key to that is the fact that you have to have a lot of data. The data has to be pretty cheap to get. It's either already available or it's very easy to get. If you don't have that kind of cheap data, then that side of it's not going to really help you very much. If we look on the other side of this plot, this is where we are with electron microscopy. There's nothing to say that electron microscopy will ever generate a huge amount of data. Most of us have been in electron microscopy for a long time. I've heard the joke about the sum total of all electron microscopy material that's ever been studied will fit on the head of a pin. Now, that might be a bit of an exaggeration, but it's clear that we're not looking at large amounts of material. We're not going to get lots and lots of data because it's very expensive. The equipment's expensive. It's hard to get time on it. You need an expert to be able to run it, and you get limited access, so it's hard to generate that data. But if we look at these two things as two sides of the same coin, what we can get from electron microscopy is we can get a set of very well-controlled targeted data, which we can then use to extrapolate up to a more general solution. So if we look at the big data of one side of the coin and targeted data on the other side of the coin, the mathematical approaches that lead to get solutions out of it are very similar. So a lot of the math that I'll be talking about are the kinds of things that are involved in big data approaches, but here we're looking at using an electron microscope, and so we're looking at getting specific, smallest possible amounts of data that we can that allows us to extrapolate up to a total solution. Okay, so in going through this approach to Inpainting, I'm going to talk about dictionary learning and how we understand dictionary learning and can use that to our advantage in scanning transmission electron microscopy. So here's our first example. It's a simple 1D image. This is the kind of thing that we teach 18-year-olds, undergraduate classes, even in high school to be able to do, which is that if you have a one-dimensional signal that's a sine or cosine function, you can do a Fourier transform, or you can basically look at the sines and cosines that make up that waveform, and you can decompose it into those elements, and those are our dictionary elements. So if we know what our dictionary elements are at any point, and we have these four very simple dictionary elements on the left-hand side, we can make up a more complex signal just by multiplying those dictionary elements by a scalar value. And in this case, we would do it with very simple mathematical approaches of a least squares fit, and work out what is the actual numbers of each of those components that gives rise to the true signal. But what we can do with that true signal is say, well, okay, let me just throw away half of that signal. And if I look at that, and now the black points are the half that remain, and do a least squares to that signal, I get essentially exactly the same solution when I've only got half of my observation. And I can keep going with this, throw away a little bit more, so we only have 25%. And if I didn't draw the original line on there, you wouldn't notice the difference between the original solution and the solution for 25%. And if I go down to 5%, you start to see a little bit of a difference, but pretty good fit for 5% of the signal. If you go down to about 2%, you start to see a little bit of a difference. But the point behind this is if we know what our dictionary elements are, and we're pretty sure that we can use those, then we can actually throw away a lot of our sampling of our more complex signal and still get a very good fit to that complex signal using those dictionary elements. So the way that would translate to a stem, of course, is to say that we could actually use a much smaller amount of sampling space to our stem image, and then still recombine it using dictionary elements to get us the full reconstructed image to come out. Now, that's easily extendable up into two-dimensional images. In this case, this is just an example of a picture from Monument Valley. The way this is usually done is that the image is broken up into smaller patches. Those patches cover the entire image, and each of those patches can be made up of dictionary elements that allow you to reconstruct the whole image. And this is the sort of approach that's usually done for image compression, of breaking things up into dictionary elements with scalar values. So if we take that image just there and look at the dictionary that comes out from the whole system, that's the thing on the left-hand side. On the right-hand side, you can see exactly what you would have to do to reconstruct that image. And there's one patch that's shown, and as you go further and further down the page on the right-hand side, you're using more and more dictionary elements, which gives you a more and more complex patch, which gives you a better and better fit to your result. But you don't always need to use all of the dictionary elements to get a good fit to the data that you have. So the more extensive we have a dictionary, the more better the training, if you like, the more complete the dictionary that you have, the more precise your reconstruction can be. But you can also get a pretty good reconstruction fit to those patches with using a much smaller set of dictionary elements, which means, again, you can reduce the amount of data that you have to give rise to your reconstruction of a full image. Now, for electron microscopy, of course, we could then extend this a little bit further and say, well, what if we had more than one image? And here's just a few more images of Monument Valley in Utah pulled off the internet. And you can say, well, actually, we could generate what would be a universal dictionary for images of Monument Valley. And so every time that we wanted to reconstruct an image from there, we could take less and less data because we would have a very good dictionary to reconstruct all of these images. Now, what that might mean for electron microscopy is then that if we could train the microscope to get the perfect dictionary for a particular type of image, then we would actually be able to get fewer and fewer acquisitions to allow us to get higher and higher resolution from our reconstruction of those images in the microscope. Now, it's not going to be easy to do that if you take images from a lot of different samples, but most of us actually work on a few set samples, and we do a lot of things that are very, very similar. And so what it means is we can start to optimize or train the instrument to actually get better and better images with less and less data from a particular sample or sample type. Okay, so the key thing then is to be able to get an image, to be able to get our dictionary, and then be able to reconstruct it. Now, there are many ways that we can look at the challenge of doing compressive sensing or in-painting to get the image to come out. And here is just a sort of a non-mathematical picture of what happens. So in the top left-hand corner here, we have direct imaging, and this is the one that we're all useful. You have a sample X, you have some kind of sensing matrix, which is an identity matrix here, and it just senses all parts on the sample and gives you an image Y. And there are the same number of pixels in the image as there are areas of the sample that you're looking at, and so there's a one-to-one reconstruction. But if you look at that, there's a lot of empty space in that sensing matrix there in terms of what you would like to look at. And so could you make that a little bit more compact? Now, this is where you go on to the things like computational imaging, which is a much more complex way of doing it. It gives you a lot more variables that you can play around with. I'm not going to talk too much about computational imaging. What I'm going to focus on are two specific cases of where we compress our imaging. And actually, I'm only going to really talk about one at the moment, which is in-painting. But there are two that you can use for electron microscopy. One is in-painting, which you can see on the left-hand side at the bottom there, which is basically saying you're only going to use some of the pixels or some of the positions in your sensing matrix from your sample. And then you're going to get an image which is much smaller, and then you're going to in-paint the missing information. The other one that's got a lot of use at the moment is compressive sensing. This is the kind of thing that Brian Reed does and IDS specialize in doing for electron microscopy, where you have a matrix which gives you different intensities, and you use that to sample your image, and then you can reconstruct again a smaller number of samples into a much bigger set of images. So let's have a look at how this works. And first, I'm going to talk about how you would do it in direct imaging. And this is something that my group used to do about 20-something years ago, of trying to improve the quality of images that are taken inside of a STEM. So here is one of the experiments that we did. This is a Z-contrast image of a very complex sample used for hydrogen storage. You can see in the middle it's got a very pretty atomic arrangement, so there are atoms all over the place, different elements involved in looking at that. And the Fourier transform, which is the transform into, if you like, the sparse Fourier space, is on the right-hand side. So what we used to do is to basically take our original image, take our Fourier transform, and because we know that it's a crystal, and we know that there are only one of a possible 230 crystal types that exist, we can identify what the amplitudes and phases are in our Fourier transform. We can look at the amplitudes and phases of all the 230 possible crystal structures that we can find, and we can then try and match the two together. And if you look at this, in this case, there are essentially just errors that come in the phases. So here they're supposed to be 0 and 180 degrees, and you can see they're either very small or close to 180 in terms of the phases that come into that. And what you can do is say that using human intelligence and knowing that really it's got to be one of these 230 types of crystal structures, why don't we impose the phases in our Fourier transform to reinvert and get a better image coming out in the other way? And that's essentially what we've done here. And so what's done on the left-hand side is putting the right symmetry into the structure, and you get a very high quality image that comes out, which is essentially denoising the process as we're going forward. Now, the thing that everyone used to ask the question at that time was, well, what happens if you get the symmetry wrong? And actually, what the right-hand side shows that if you get the symmetry wrong, what you get is artifacts in your image, and those are asymmetries in the reconstruction. And people always ask the question, well, would you ever be able to identify that? And actually, for those of us that do a lot of atomic resolution imaging, asymmetries in terms of the images and what comes out are actually pretty easy to identify. And if you didn't want to trust that, you can always go back to a fit and you can select what goes in and try multiple symmetries to pick which is the best one to come out. Now, that's the way that we would do it if we did it all by hand. What we're going to do now is to say, right, let's take our in-painting approach and say, well, could we get a computer to help us with that? Can we get a computer to say, maybe we don't need all of those pixels to be able to get those phases to come out? Right? If we think about that image that we had all the way back here, we don't need all of those pixels to get a Fourier transform. You can get a Fourier transform for a much smaller number of pixels in our image to be able to get that to come out. So effectively, can we look at something where we do a similar thing, but we use what we know about the sample, what we know about the symmetries that are involved, and in-paint our sample automatically using a set of algorithms to do that. So here we have our in-painting idea. It's taken an image of strontium titanate grain boundary. The reason why it's taken from a grain boundary is because the grain boundary doesn't have the same symmetry as the grains. And so the first question when we do in-painting is usually, do you need to have something which has symmetry? Is it crystal? You have to use a Fourier transform to get the reconstruction to work. And the answer to that is no. You don't have to use Fourier transforms to get it to work. We do that in a lot of the demonstrations that we give for why in-painting works, simply because most people are familiar with Fourier transforms. And if you explain to someone what a Fourier transform is, or just say that you're doing a Fourier transform, most people can follow what you're talking about. So in this case, we've got a grain boundary. We've taken a subsampled set of images. This is the dictionary that's actually taken out from this subsample data set, and this is the reconstruction that comes out. And in this case, what we've used is beta process factor analysis, which is a way that we can actually get a dictionary out from a set of subsampled information. And that's the important part of it. I'll get back to that briefly in a minute of the way that we do the process of getting the dictionary. But the idea is once you've got the dictionary, you can get the reconstruction. Now, nobody here will say that the image on the right-hand side is as good as a fully sampled image of strontium titanate would be. But we have to remember in electron microscopy, the reason why everyone takes images of strontium titanate is because it doesn't damage. And so it's very, very easy to image with high precision. In the cases where you've got things that will damage a little bit more, then it's much harder to get those things to happen out. And so this approach will enable that to help. All right, so in this process, what we've said that we can do here is that we can take a set of subsampled images where we're only taking a small number of pixels, and from that we can reconstruct the full image to come out. Now, why would that be a good thing to do in STEM in terms of what happens in the dose? Now, I've talked about this quite a few times in the past, so I'm not going to go through too many of the details of dose and what happens inside of the STEM. But we can think of the damage that happens in electron microscope as there is a primary event that takes place when the beam hits the sample. Not all will damage, but when it does, nucleates from a point, and then it diffuses out through the sample. And so we get diffusion away from a point. Now, when we have a step separation in the stem, then we will go from one point, which we have over here on the left-hand side, to another point at some distance away. And this is our scanned point, from point to point as we go across. If our scan is not moving far enough, then the nucleation of defects that we have at each point due to beam damage will start to overlap, and we'll get a blossoming or growing of the damage effect that we have in the sample. And so each one can actually interact to make a more deleterious damage effect. Now, we know that this happens in STEM all the time, and it's something that is inbuilt into the way we operate the microscope. If someone is used to doing STEM and they want to get to a point where they have less beam damage, they turn the magnification down. What turning the magnification down does, the probe size stays exactly the same. It's still 1 angstrom if you have an aberration corrected microscope. But when you turn the magnification down, you increase the spacing between the probe position. So the pixel size is much bigger than the probe size. And so as you scan, you're never really hitting the same point again. And so the damage appears to be less because we're not actually looking at the same places and the pixels are not overlapping. The other reason that this happens a lot, and we know that it does, sometimes when you take a slow scan in STEM, when you're trying to get the best image, so your dwell time is too long, as you move the scan down and you're acquiring your image, when you get to the bottom of the image, you get something where it's more damaged than the top of the image. And that's because the probe is pushing the damage in front of the probe scan, which is accumulating more and more as the scan is going forward, and that's damaging further down. In the days when we used to do line scans across grain boundaries and interfaces for compositional analysis, you used to be able to push the defects ahead of the beam. So you'd have a line profile going to a grain boundary, and then you go across the grain boundary, and on the other side, it would be completely flat. And the reason for that, again, is the overlap between the beam is actually pushing the damage around. And so in addition to having a dose effect, in addition to having a dose rate effect, you also have a dose overlap effect, which is affecting your ability to be able to get good images out of STEM. Now, if you go and look at this mathematically...
Can I ask you a question before you move on from there?
Yep, of course.
I could imagine two different effects with two different time scales. One of them is you're making diffusing species, and then those diffuse and interact with one another, and that's maybe microseconds to hundreds of microseconds, depending on the diffusion rate. And then the other one is you make some species, and then you hit the diffusing species with the beam again. Mm-hmm. And that's now sort of nanoseconds for the transit time of the beam through the sample. Do you see both of these? Is one more important than the other? Can you say anything about that and the time scales that might be involved?
Yes, so nanoscale is very important. I'll just get to that with this slide here to answer your question. But the real point is it's all important to the overall damage that you get in your system. Now, if you think about something that we would intrinsically say damages quickly, that process of the diffusion is occurring much quicker than in a sample that you say would damage much more slowly, because we know that if you put the beam and you stop it on a sample that damages quickly, that damage will propagate a large distance. It won't just be focused at the point where the beam is. If we have something that we would say is beam tolerant, then what that's saying is the rate of the diffusion of the damage is much slower, and so that we can basically get to that point where we're not creating as many damage effects and they're not diffusing as quickly. Now, what this gets down to is basically two numerical factors that you can put into a differential equation to work out what the effect of damage is. And you don't really, at this point, need to know whether it's ionization damage, whether it's knock-on damage. It's just a damage effect that's taking place that will be diffusing away from the point of incidence where the beam is. Now, in future, as you go through this, then it should be possible to use that same equation to actually get some of the numerical values out for diffusion of damage and creation and all that comes out of it. But for now, what we're just using it as a way of doing is to saying, okay, you have these two values, which is the creation and the diffusion. And if you put that into a differential equation, you can either put approximations in, which Joe Verbeek's group did to work out what the effect of damage is, or you can try and solve the whole thing numerically, which is what we've tried to do. Supporting this idea of diffusion being important in terms of what is happening to damage, a lot of the people that have tried to do pulsed electron beams to look at the damage in liquid cells and in materials find that there is a healing effect that takes place. You pulse, you wait, you pulse again, and your cumulative dose can be a lot more than what you would have if you had something which was continuous beam. And that's a very similar kind of idea to this, which is that the diffusion can propagate away and you're not hitting on top of the whole thing. So anyway, you can mathematically go through this. You can show that if you have a complete scan, that's the worst case in STEM in terms of the overall damage, which is pretty much the same as doing a TM experiment, because in your TM experiment, you have all of the pixels being illuminated at the same time. And really what this is saying is that what you want to do is to have the biggest time and spatial distance between your experiments each time. So the biggest gap temporally, the biggest gap spatially means that you're in the best condition. Now, you still may not avoid damage. Things may still damage because they just happen to be a damage threshold which is less than the dose you're putting in there. But what that's doing is making the damage as minimal as it could be during the experiment that you're trying to do. And this is actually something that Ken Downing actually proposed back in the 90s, where he called it spot scan mode for cryo-electron microscopy, which is he would just move the TM beam around over the sample, getting it into the lowest dose he could in each particular area and acquiring the beam at that time. So it is something that is sort of known in the STEM and the TM community. This is sort of an attempt to try and classify it in a way that allows us to make the experiments work. Now, I'm not going to talk about the math in the way that this goes. All I'm going to say at this point is that in all of the simulations, unless otherwise stated, we use BPFA to get the dictionary. And that's because BPFA allows you to do it from a subsampled image. So you can get a fully sampled dictionary from a subsampled image. And so all of the approaches that will be using BPFA. Okay, and then this is just an example. I've shown this many times before, but it's still a nice example of the subsampling. This is something that was done at the SuperSTEM in the UK. The left-hand side is the fully sampled image, and yet you can actually start to see damage coming in the fully sampled image in certain places. And if we go to the subsample, then we can reconstruct the image from 1% of the sampling. And here you can actually see the images drifting up to the top left-hand side because we've actually changed the thermal and the electrical equilibrium here by having lower current and less of a thermal load on the sample. But we can still get the reconstruction to work. Okay, now you can prove this, and we've gone through and shown that the experimental validation of the CS, the compressed way of doing the in-painting for the STEM works. And in the sample that we did for the experiment here, which is looking at a semiconducting sample, it was better than the low dose full sampling for the reconstruction. Now here it's very important to understand that this is with damage that comes into the system. Under normal conditions, you should not be able to get better from the compressed sensing and the in-painting than by subsampling at low dose. But the difference is here is that we can control the dose to the point where we can get a better result when we go through the whole system. And this is much similar way to thinking about the way that cryo-EM advanced when people use CMOS detectors. What the CMOS did is they could acquire for shorter durations, and just before you got damage taking place, you just made the image about the high resolution and you didn't have the damage coming into the system. That's what we're sort of doing here with the subsampling. It's at the point where you're not nucleating damage, and so because of that, you get the high resolution signal, and then you can do the reconstruction. So if you get the cases right in terms of the dose that you put into it, then you can get a better reconstruction from the subsample. Okay, so that's where we've been for quite a while. What we're trying to do now is to say, well, okay, so we've got this dictionary. How important is it for you to have the correct dictionary to get your reconstruction? And so what we have here is, this is an image from the University of Warwick, has a STEM data set that you can download just to check. And this is obviously Barbara on the right-hand side. And if we go through the process here, and you just use whatever method you want. I don't think this was done with BPFA because it's not subsampled. So we can get the dictionary, and you look at the dictionary, and it's sort of as different as a dictionary as you could possibly get for an experiment. The one from the STEM image is all circles, and the one from Barbara is all stripes. And so you say, well, different dictionaries, were they going to work? Can I use the dictionary from Barbara to make the STEM image, and can I use the dictionary from the STEM to make the Barbara image? It actually turns out you can do that with the dictionary to make it work. And this is just showing here how you use the Barbara dictionary to make a circular atom. It takes a little bit more effort and a little bit more iterations to make your dictionary work, but you can transfer the dictionary from one source to another and get the dictionary to work. I'm not going to show it here, but you can also change the magnification of your image in your dictionary so that you can take a dictionary from a low magnification image in a microscope and use it to reconstruct a higher magnification image. And what it means is that we can transfer the dictionary from one image to another and still get a reconstruction. The important thing about this is that when we use the Barbara dictionary to create our image from our electron microscope, we don't get Barbara in our electron microscope image. There's not a transfer of the information in the dictionary into the image that you're reconstructing. So that means if you're going to transfer dictionaries from one image to another, it's not that you're going to be taking information that was in that dictionary and putting it into your image. It's still reconstructing your image from the data that you have. Where that can really help is by looking at hyperspectral images. So here's an example. This is actually an SEM set of images. The image at the top is a backscattered electron image. So this is your standard detector from an SEM, very high resolution image you can get out from it. Lots of contrast, tells you about the grains in the sample. What's in red is one channel from an EDS map. And in this case, it was the aluminum channel. Now, if we zoom up to the area, this is taken hundreds of millions of pixels, very large area scan for the EDS. And if you zoom up to a particular area and you look at the picture in the middle, you have here your EDS map. Because the dwell time has to be very small to be able to get a scan over this large area, that EDS map at that magnification looks a lot like a subsampled image. It looks like we're just missing some pixels. And that's, of course, because the cross-section for scattering is small. And so with that small dwell time, some of the pixels will look black. But it means we should be able to in-paint that missing information from our backscattered image. What's more, because we've got this wonderful, very high contrast, very high resolution backscattered electron image here, we should be able to use the dictionary from our backscattered electron image to in-paint our EDS map. And what we've done there is then get a much higher resolution or a higher signal level with better contrast and better resolution from our EDS map by using this approach. So here's what it looks like. Here is a high resolution backscattered electron map that you can see on the image on the top left-hand side. That's the dictionary. In the middle at the bottom, that's what the low signal EDS map looks like. And when you use the dictionary from the backscattered electron, you get a much higher resolution reconstruction of your aluminum map. And here we haven't done any post-reconstruction sharpening, which would deal with this little blur that comes in after all of these reconstructions, but it is possible to do that to make it come back to a much sharper image. But what you can see is actually in this EDS map now, we have all of the surface effects that are in the backscattered electron image. So effectively what we've done is create a much higher resolution EDS map, which is kind of like a hybrid EDS backscattered electron map. So we're now creating different forms of contrast. We're getting much higher resolution out of the whole thing, get a factor of 100 to 1,000 increase in sensitivity in terms of the precision of your composition analysis that comes out of it. And you get a map that shows you all of the surface effects that you have also in your backscattered electron.
I have a
question.
Sorry. So there's a question.
Now, if we can do that,
you have to be really loud. Go ahead.
Yes, so I was wondering, like, I mean, the backscattered electron excitation coil is much smaller than the X-ray one in the EDX images. Yes, so basically it means there is, in the actual EDX images, you have contributions from beneath the surface and it's much broader. Yes, basically you're transferring sharpness information from a different kind of excitation coil to the EDX image. Yes, so in theory you would need to do some sort of deconvolution, which you don't do here. Yes, you just Inpaint.
Absolutely. If right, so it all, but the amount in an SEM of the volume depends on the beam energy that you're using to form your image. So at this stage, in terms of the dwell time of the map, effectively we're not. If you look at right, so down at the bottom here, this is what the map looks like in real times. This is what is the best EDS map that money and detectors can buy you at the moment if you want to do a fast scan. What I think you're talking about is that because the backscatter electron is coming right from the surface and the EDS is coming from an interaction volume deeper, then there should be a resolution mismatch between the backscatter electron image and your EDS. And that's absolutely true. But there are ways you can deal with that. But the reality is in this case is that this doesn't have any resolution in it at all, really, in terms of what's in the real map. So effectively, that's a second order fix on the problem. The real problem is to get an image with our compositional map having the sensitivity to be able to know what the phase is. And then we have to worry about the mismatch at the end if we really wanted to get them to be exactly the same resolution. Yes, I think that answers your question. Is that right?
Yes, partially. I mean, the X-rays will also actually include subsurface effects, yes, which the BSE does not.
Yeah, but effectively, the interaction volume depends upon your energy of your beam, whether how deep it goes. So you could manage that and work out what that reconstruction should be. Okay. All right. So, and I'm sorry, it's really difficult for me to hear when even if you're shouting at the microphone, I can hardly hear you. If I didn't answer your question at the end, ask again, or just send me an email or something, and I'm more than happy to answer. So now, if we've got that, you can say, well, what that's doing is saying that if we've got something that has lower noise, we can get a better reconstruction. And we just submitted a paper on simulations where the poor students got absolutely hammered by the referees, and I think we're missing the point in terms of what we were trying to get out of the simulations. What we're trying to say here with the simulations is that if you had a stack of images that you were trying to work out the dictionary for, if you take your simulations, at the moment the way simulations work is people try to match the simulations to your image, and you don't know all your imaging conditions precisely in high resolution TM. Even when you're doing SEM images, it's not perfect in terms of the interactions. And so there's a certain amount of matching with different conditions that are concerned. If you do it this way, you actually don't have to match the theory to the experiment. What you do is to say, well, I'm just going to do a simulation. It doesn't have to be perfect. It could even be a subsampled simulation. I don't have to do all of the different frozen phonon configurations because at some point of the image, it will be fine. And I'm going to solve that simulation in the same stack of images as my experiment with much lower signal to noise is. So what that means is that the dictionary that's being developed will work for the simulation and the stack. So it's actually solving the set of them together. So rather than matching theory to experiment at the end of doing the experiment, it's actually using the theory to help seed the dictionary, which again, because you have a quantitative use of a dictionary to do your reconstruction, your best fit, you're able to then match the dictionary or match your simulation to your experiment at the same time. So it takes the workflow in terms of the matching of the simulation to the experiment and integrates it into the acquisition of a low signal instead of making it trying to match a low signaled image to a very high signaled simulation, which is very, very difficult to do. Now, this can go into many different strategies that you can do with this. You can go through all kinds of different dimensionality all methods where you have 1D, 2D, 3D imaging. In principle, I think we can get a 7-dimensional image out of this, which is an energy filtered, time resolved, 3-dimensional tychography data set. Now, the important thing about the Inpainting is that each of those dimensions are not completely independent. So every time you add another dimension to your data set, you can actually decrease the amount of data points that you need for each of those dimensions, because they're not completely independent. They're looking at the same sample, you're Inpainting the whole thing together. So if we can do that, then you can go ahead and do a whole bunch of different things. And I'll just blast through this pretty quickly because I'm running a little bit late. You can go through for your spectra, you can help to denoise your spectra, get increased signal to noise. When it comes to doing tychography, you can also do subsample tychography, and you can reconstruct that pretty well from the subsample data set. You can even subsample on the image as well and be able to reconstruct that. As a final example of doing this, one of the things that I said at the start is we also want to affect our ability to do specimen preparation. So here is a cryo-fib slice and view of a biological specimen. This is the full image on the left-hand side. This is the reconstructed image on the right-hand side. In this case, it was only 25% of the data, so it wasn't really trying to push the limits of the resolution. It was more about looking at the fidelity of the reconstruction and the fact that we can denoise the data set as well with our random sampling to go through it. Now, in this case, we are just reconstructing each slice as a 2-dimensional reconstruction, but actually we should get increased precision on a lower data set if we deal with it as a 3-dimensional reconstruction, which is the next set of data that we're moving through. Now, in the case for specimen preparation, what we actually want to do, there's a time for slicing and there's a time for imaging. What you'd really like for your subsample is to be able to reconstruct your images quicker than the amount of saving that you get from using smaller numbers of pixels, right? So the simple math is that if we have 1 million pixels in our image and we have a 1 microsecond dwell time, it's a 1-second image. If we're using 10% of the pixels, then we're going to get something which is only 1/10 of a second. But if it takes us 2 years to reconstruct the image, then it really doesn't help that much. So what we have to do is to get to the point where we have real-time reconstructions. So I've just got an example here, and I apologize for doing it as a download here from what's running on a computer. The reason for doing that is because every laptop, when you start to run one of these things, is actually using some of the memory to deal with the projection of the image and not the reconstruction. And so the only way to see a true amount of how quickly the reconstruction works is by actually looking at the thing running side by side with the real image. So this is looking again at these fib sections. The left-hand side is a 1.25 million pixel image, and on the right-hand side is the reconstruction that's coming out. And this is actually running live in the computer for a reconstruction. So we have 25% of the pixels on the left-hand side. The reconstruction is running at the same time as this is loading in each of these slices. So you can see the frame rate is essentially running the same way. It's not running as fast as we would like because part of the processing speed is to spit it out and show the frames. But here we have a reconstruction of a 25%, 1.25 million pixel image that's running at almost 2 frames per second. So now we're getting to the point where we can get real-time reconstructions. Now, we can do even better on some things. And so here is it. Oh, sorry, that didn't work. Let me go to the next one. Okay, here is an example of a webcam. So this is a color image. And doing a very simple reconstruction. This is Alex, the student who codes all this stuff up. The left-hand side is our subsampled webcam. The right-hand side is the reconstruction. And you can see how long it takes the reconstruction from the difference between the images that you can see going subsampled. And what's happening here is the subsampling rate is going lower and lower. This is using just a simple local means reconstruction. And you can see it's slowing down the actual webcam to get the reconstruction to work, simply because the algorithm has to work a little bit harder to get the reconstruction as you go down to 10% of the data. But still, you can see this as a frame rate that's moving. Now, if we go a little bit further and run BPFA, with BPFA, as you get going, it actually gets faster. I'm sorry, Alex didn't turn his microphone off here, so there are a few noises in the background. But this is just running BPFA, the same webcam, now in real time, shows the dictionary. shows the BPFA approach, shows the reconstruction that we can get out of it. So it's again going down to lower and lower sampling rates. But because it's BPFA and we have more and more images as we go, the reconstruction actually gets quicker as you go in time. So as you go to smaller and smaller sampling, as you go to more and more frames that you have to make your dictionary, your reconstruction actually gets quicker and quicker the more you go. So we can now get down to about 1% of the pixels and get the reconstruction to work pretty well. Now in this case, this is just run on a normal CPU laptop. This is Alex's University of Liverpool laptop, which cost £300. So it's not got the greatest processing speed to go through that. If we think about how we should be able to go moving forward with GPUs that are optimized for the process, and we should get a factor of somewhere between 10 and 100 faster, that puts us into the video rate up to 100 frames per second for our reconstruction as we go. So now we're at the point where we can actually get the reconstruction to be faster than the amount of data that we've saved by going to the subsampling. And so with that approach, we can now do live scans and things like that with subsampling at the optimal dose control.
I have a question.
Yep.
So, like the reconstruction looks really good. I'm wondering whether this makes sense or not about, because for instance in Alex you can see, or like you go back and you go back.
Yeah.
So you can see right now you have a video, right? But like in microscopy will be interfaces. So I'm wondering whether you lose spatial resolution at the boundaries, or like the sharpness of what you will be able to see, or not.
No, as long as you have a certain sampling at that interface, then you wouldn't lose the resolution. Here, if you look as it goes to lower and lower sampling, because of the BPFA approach to the reconstruction, it actually doesn't lose resolution and it gets faster as it goes. Obviously, we can't go down to zero sampling and get a good reconstruction. There is a limit to how much you can go. But the approach seems to get down to somewhere between 1 and 10% of the sampling and still get the spatial resolution that comes out. The idea about being faster on the reconstruction is, let's say, again, we use 10% of the pixels. So our first image takes us 1/10 of a second. If it takes 1/10 of a second to reconstruct, we can then use that reconstruction to position the beam for the second set of pixels. And so again, we can have 20% of the time we can target to specific targeted pixels of areas where you think there's missing information. And all of that can be done in real time. It's sort of what's termed as an adaptive sensing approach to the whole thing. But the key is the speed. If you don't have the speed, then you can't get to that point. Okay. All right, now some of this also means that, and I've shown this before at several meetings, so not focus on it, but if you have the ability to enough information to reconstruct a full image from the number of samples you have, then you also have enough pixels to be able to run analytics. And this is just showing on a subsample data set of a real-time image of deposition of lithium onto an electrode, that you can actually see the analytics running quicker than your eye sees the lithium being deposited. There's obviously a bigger error bar at 1% sampling than there is at 20% sampling or 25% sampling. But essentially, your analytics can run quicker than the human eye can get to, and so you can actually go through and see all of those things. Okay, so the way that we do this in practice is we can put this box. This plugs into an external port on a microscope. Every microscope has an external port used to control EDS detectors. So you can plug it in. This one comes from direct electron. Here's an example of an in-situ experiment. We took 3% of the data, and the bit on the right-hand side was the reconstruction. If you look at the experiment when it was full sampling, 25% and 12% sampling, and all the way down to 3% sampling, you can see there is a morphology of the particles that are nucleated and grown in this liquid cell experiment, depending on the way the sampling was done. Where the beam stayed the same, it was just the amount of sampling that went into it. Now, in this liquid cell experiment, this is deliberately damaging the liquid to create the nucleation of nanoparticles. So this is the kind of thing that occurs in a damaged experiment. And so what happens is when you look at the difference between fully sampled and 3% sampled, there's a different type of morphology for the nanoparticles that comes out in 100% sampled and at 3% sampled. And the difference between the sort of round homogeneous particles and the flat particles is much smaller when you have a 3% sampled compared to 100% sampled. And when you actually put them on top of each other, actually those flat planes come really easily, the homogeneous come really easily unless you have all of the big amount of dose that goes into the system. Now, the reason why that happens is because when you have one of these liquid cells where you have an insulating window and then your water with the nanoparticles in there is somewhat conducting, not perfectly conducting, but more than silicon nitride is, then you get a buildup of secondary electrons. Those buildup of secondary electrons are basically giving you an enrichment on the surfaces. So all the nanoparticles are growing on the top of the bottom surface when you have a high dose. If you turn the sampling down, so again, you've got a bigger distribution between when the electrons go in and how much they go in, then you change the overall distribution that's taking place and you change the kinetics of the reaction. And this is exactly what we would expect to have in all of the damage experiments that we see for the high resolution for the in-situ going forward. Now, I've used up all my time, but I had some more stuff I was going to do. I'll quickly say that we've actually designed and are buying a microscope to do all of this subsampling directly. This is a new JEOL microscope, 300 f2 grand arm that will be coming. It was January, now it's April because we can't get the room ready in time. But it will be CS corrected in STEM, have a lot of the IDES controllers in there, the direct electron free scan, dual EDS system, and also 3 CMOS detectors. So we can do energy filtered ptychography, we can do low dose EELs, we can segment the beam, we can do modulating the dose that comes into that, we can put that with the scan coils so that we can have control of the dose in the way that the system will go through. With the EDS and the EELs together, we should be able to do essentially these hybrid type imaging maps that we would have of beam sensitive materials. So you should be able to get atomic scale results that come out of that. With the luminary system from IDS, we should be able to do optical excitations to look at excited states for the things that will be happening. There's no real transient effect that we're looking here because we don't have the temporal resolution on this, but we can look at illuminated samples to look at changes that will be happening with that. And then all of this will have a set of holders, cryo, liquid, gas, open cell, straining stage, heating, and vacuum transfer. So we can look at all of these effects and how the beam interacts under a wide variety of different conditions to really get a better handle on controlling the dose so that electron microscopy can move away from standard samples and into the kind of exotic samples that a lot of material science is working on right now. The final thing I wanted to mention is that this is also going to play into a new national facility that we're building in the UK. This is called RUEDI, which is Relativistic, Ultrafast, Electron Diffraction and Imaging. It's essentially a 2 MeV imaging system, 4 MeV diffraction system that will have 100 femtoseconds or shorter temporal resolution. Compared to other systems in the world, it will have lenses so that we can do imaging. The really important thing for electron microscopy is at 2 MeV, you can look at much thicker samples, and so you can look at things which are more realistic of the real system. It's built in the UK. This is what the thing can look like. So it's going to be, this is not really a microscope, it's horizontal. It's about 15 meters long. It's going to cost about £50 million to build. But at the end of it, we should be able to do a lot of dynamic experiments where obviously a lot of this compressive sensing in-painting stuff fits in. I'll just go through lots and lots of different science. Angus Kirkland is part of this, and Angus is there. So if you want to talk about RUEDI, Angus will be able to answer all the questions you might have on that. And then it fits in with the data infrastructure. We will do a digital twin, compressive sensing. So the idea, we get the analytics out at the end. So you get hypothesis, image-free hypothesis testing will come out, linked with the Hartree Center at Daresbury. I think that's it. Okay, all right. So we've got all of these things that we can do with in-painting. It helps us to control the dose. We can look at different kinetics that come out of it. The system we have set up is trying to do it for everything from fib all the way through, because if you think about what fib is. Fib is a deliberate damage mechanism that's taking place. If you control the fib beam in the same way so that you have a partial scan with the fib beam, you should be able to change the dose distribution from the ion beam, which will allow you to have more precise cuts with less damage in principle. So we're going to test that. Also, we have a new fib coming to Liverpool. If anyone's interested in looking at this stuff, we have a free download of an old version of the code. It doesn't have any of the speed involved in it, but you can put images in, you can test it, you can download it from the Albert Crew Center at Liverpool. And we have the latest version of the code up and going now. And if anyone's interested in trying it out, which has the speed involved and actually putting onto a microscope, if you just want to send me an email, we can try and go through all of that. And then finally, all of the people involved in this, people at Liverpool, Rosalind Franklin Institute, King's College London, the original work which is done at PNNL, and then the SuperSTEM, and we get a lot of that EDS collaboration with Oxford Instruments. And with that, I shall finish, and thank you for your attention and take any questions you may have.